We are officially moving into kind of a new mechanism, which is our nucleophilic addition followed by elimination, which introduces new functional groups. The new functional groups that we get, as far as our nomenclature goes, is really just our acids and esters. We will see the amines, and we will see the acyl chlorides, or the acetyl chlorides, but for the most part, it's just the acids and esters that you have to worry about. Acids are the highest priority on our list. They come in at ic acid as the ending. Esters can be the highest. I'm not sure what that's attempting to show there, actually. So I'm going to erase that part. Esters usually come in as OHs. So you would name them similar to how you would name an ether. So like an ether, you have diethyl ether, okay, or methyl ethyl ether. You list the substituents and then name the oxygen. The same kind of thing happens with esters. We'd call it methyl ester. There's a methyl group connected to the oxygen of the ester functionality. Kind of make sense? So that would be our ester. That would be a methyl ester because we have a CH3 connected to it.
And what would you use for the O8? Like how would that?
So the O8 would get named. So in this case, how many carbons are in the O8 part of this? One carbon. Okay, that one carbon will dot as blue. So this would be kind of a weird one. This would be a methanoate. Okay, because there's only one carbon there. So it'd be a methanoate. Would be kind of your core root name. We could switch it up and add an extra carbon to it. All right, that's a little bit easier because now we have we still have a methyl ethanoate because there's two carbons in the OH portion of it. Okay, so this portion is our OH.
I'm sorry, why is the methyl first?
Because it's a substituent.
Is it attached to the ester? Or?
How can I not write that? Oh, I had it right that time. The methyl comes first because this is a substituent.
Of the ester.
A substituent on the ester functionality. Okay, so just like normal substituents, it gets listed out front. Okay. They don't get tested quite as frequently, probably because they're more complex as far as names, but it's always nice just to mess with people. So here's some practice. We'll give you 4 minutes. Come up with the most you can. Okay, so that's an ester, so two carbons, an ethanoate, and the substituent on that ester is a hydrogen. So it would be hydrogen ethanoate.
No. Ethanoic acid.
Okay, why would we call it ethanoic acid and not based off the ester name? A carboxylic acid has inherently different chemistry than an ester, so we want to go through and specify that. I'm not going to erase that name because that name is going to become important later on. Okay, so I'll just put kind of, come on, fine, I'll just put a blue line through it. So we could call this ethanoic acid because it has two carbons in the backbone. There's another very common name for that substance. Acetic acid. That is a much harder question than I can answer right away. In purple, that's known as an acetyl. Okay, an acetyl functional group. When I attach an OH, that becomes acetic acid. We change the ending. So it goes from an acetyl to acetic acid. Which of those two names should you know, ethanoic acid or acetic acid? Yeah, it depends. Officially, it's ethanoic acid. That is the IUPAC nomenclature system, and that's what you're responsible for according to ACS guidelines. However, acetic acid is such a common name, you will see acetic acid. Okay? You should know both, unfortunately. So, and this has popped up in a few cases before too. The common names are dangerous. You're not officially responsible for them, but they are so common that chemists will inadvertently use them without thinking about having referenced a common name as opposed to the official name for it. Okay? And before you get too freaked out on that, what is dihydrogen monoxide? Water. Why do you not call it dihydrogen monoxide? That's stupid, okay? You're referencing the IUPAC name, dihydrogen monoxide, versus water, the common name. You've memorized the common name. It's hard for you to get adjusted to trying to switch a new name. The same thing is happening for chemists. Okay. The next one. Yep, I was being a little bit misleading. A couple people were like, well, why'd you write hex? It's not 6 carbons. The longest carbon chain is 6 carbons, and conveniently it's drawn in a nice kind of straight line to make you think that that would be the primary chain. But what do you have to remember? You have to remember the priorities of your functional groups. The longest carbon chain must contain the highest priority functional groups. The highest priority functional groups would be the carboxylic acid at position 1, because it's the highest priority. 2, it needs to pass through the alkene. 3, 4 to the aldehyde, which means we're not looking at hex, we're looking at bute. Okay? To now decide on the next part, because I started to hear people jumping to the rest of the name. Butanoic. Okay? Well, butane, AN, means the carbon chain is all single bonds. It's not single bonds. We have an alkene, so we need a butene, but we have to specify where it's located. It's at position 2. Okay, now that we've got the ene, we can drop in our oic acid. Do we have to go through and put in, or should we put in a 1- oic acid in there? We don't need to. Okay, depending on who you talk to, I think IUPAC is starting to shift towards saying that it should be written in there. Okay, this gets kind of at the common versus official rules. The reason why it should be written in there is to be extra specific in where it's located. Okay, but it is typically not written there because the carboxylic acid, by definition, is at position 1. It's either at position 1 or position end of the chain. There really isn't a difference. Okay. And the only reason it would be at the end of the chain was because there were 2 acids, because the acid has to get number 1. So if it's at the beginning of the chain and the end of the chain, we'd have to number both. Okay? So but-2-enoic acid, that covers the double bond. It does not cover the aldehyde. And if we remember, the aldehyde from the last unit should end in Al, but that assumes the highest priority. It's not, because of the acid, the Al becomes oxo. It's now a substituent in the middle of the structure. Okay, and where does the oxo show up? Position 4, so a 4-oxo. Do I have another substituent? Okay, I have a propyl, and it is at position 2. Putting the name together, and this is why I had to pause on writing the oxo, it's going to be Y4-oxo-2-propyl and not the other way around. We have to have alphabetical. 4-oxo-2-propyl but-2-enoic acid. Okay, is that now the proper full name? Preeti? No, it's not the full name because we do have cis-trans isomers. We do have to worry about the EZ. Okay, when we look at the double bond at position 2, is that a cis double bond or a trans double bond? That's 6 or cis. All right, can I clear all the work over the top of it? Some people gave me are looking weird. Yeah. Okay. Let's clear all the work. Let's go through our cis-trans rules again. Okay. Split the double bond in half, perpendicular to the double bond. Look at each half. That carbon versus that carbon, which is higher priority? Top or bottom? Top, because it's connected to oxygens, the other one's connected to carbons. So that gets the higher priority. We'll go ahead and star. We move to the other half. We're looking at hydrogen versus carbon, which has the higher priority. Carbon, because 12 versus 1. It's, yeah, you're right. Higher atomic mass. Now we can cut it parallel to the double bond. Where are the stars? They're on the same side of that bond, which means cis Z on Z same side, 2Z. So 2Z, 4-oxo-2-propyl, butene 2-enoic acid. Okay, when do we have to worry about the ZE system? So there are two good answers to that. One, recognizing that we have cis-trans isomerism as a possibility within the structure. Okay? That is your absolute truth answer. That's when you should evaluate cis and trans. But knowing your instructor hating to grade nomenclature, shifting nomenclature to strictly multiple choice, when should you worry about E and Z nomenclature? When you look at your answer choices and you see E and Z show up at least once, you should now be thinking about, do I have to worry about it? Okay? Lower left-hand corner, I actually did this one correctly, ethyl. So we're naming the two carbons as a substituent on the primary functional group. Okay? The primary functional group is an FNO8 because we don't have a hydrogen out there. Okay? So that's just your standard ester. So far, so good? Last one. How do we look at that one? What's our functional group there? An ester, but I thought esters were bonded out to carbons. That's not bonded out to a carbon.
No, you have potassium.
It's not a carboxylic acid because it's a potassium, not a hydrogen.
So you can say potassium butane.
Right? So the way this compound gets named is like an ester. Okay? We'll reference the substituent, which in this case is potassium, connected to a butan O8. Okay? So if we think about that very first name that we looked at and we said that was a horrible name to use, hydrogen ethanoate, esters, as a rule, follow that same pattern. What's the substituent on the ester functional group? Why do carboxylic acids get a different nomenclature system from the root ester name?
Because it has an alkyl group versus
It has to do with the reactivity of the molecule. They're acidic. The chemistry is now changed so significantly that we're addressing that the chemistry has changed by changing the name. Okay? So there's a reason why we're shifting away from that kind of ester pocket of naming. Kind of makes sense? Is there a question, or are you guys good? Okay. Trying to be good? Get it? Okay. Nomenclature requires practice. You should just keep going through and cranking a bunch of other ones. I agree with you. It sucks. You just got to deal with it. Okay. Just because nomenclature sucks, might as well look at some more. What's going on with those top two? What's the functional group? Okay, those are amide functional groups. Okay, well, we didn't talk about how to name amides, so how could we possibly go through and name these? Okay, well, let's try and process through them. If this is the amide, well, how many carbons went into the amide? 2 carbons, purple and purple. So we have an ethanamide. Okay, we could say, well, isn't there a third carbon? Is the third carbon going into the root structure of the amide? No, just like the ester, it's coming in as a substituent. So I will now reference that methyl as a substituent on the ethanamide by putting it out front. Okay. We could now run into an argument of, well, where is the methyl connected? Okay, by just sliding it out in front, we're saying it's connected to the ester. Is that an ester? No, it's an amide. So I want to be more specific about where that methyl is located. What atom is that methyl connected to? Nitrogen. N-methyl ethanamide. Okay, so if you've ever seen a name with the N in it, that's why the N is there. The N is the locator. Okay, when we move to the next one, what's different about it? In the upper right. There's now 2 methyls. So instead of it being methyl ethanamide, we could call it dimethyl ethanamide, but I have to reference the location of every single group because there's 2 methyls connected to the nitrogen. I'll call it NN, dimethyl ethanamide. Do I need to write that one down? Do we have to call it ethanamide? Is there another name we could use? Whoops. So the acetyl would be a substituent, but it's part of the amide. So it's no longer acetyl, it becomes acetamide or acetamide, however you want to say it. Okay. Bottom one, that one should be relatively straightforward. Acetic acid, what becomes the next one? Okay. The functional group, which we will reference a whole bunch, that functional group is known as an anhydride. Okay, why is it an anhydride? The equation balanced? No, to balance it, what would I need? Touche. What stuff would I need to add to it?
Dimethyl? Or, yeah.
I need another methyl, but I also need another carbonyl. It's the exact same structure, just duplicated, 2 of those, but then I have too many oxygens. Water left the structure. Because I've removed water, that structure is without water. That's why it's called an anhydride. It's referencing the removal of the water. How do I reference the rest of the pieces? Okay. In this case, we would kind of name what those pieces were. What is this piece?
Acetyl.
An acetyl, so we have acetic anhydride. Oh yeah, no, that's right. Sorry, it just all of a sudden didn't look right. Acetic anhydride, why are we calling it the ick? Because it came from the acetic acid. Okay. You don't see those as often, don't stress about them, but the anhydride is the important piece in the middle to recognize. Okay, and recognize where it's coming from. The anhydride is effectively 2 acids reacting with each other with the removal of water. Okay? Kind of, sort of? Okay. Spectroscopy, everybody's favorite. Because we're looking at our acid derivatives, just some kind of clean, big things to talk about with our IR. Our carboxylic acids typically have the carbonyl and a broad OH. That OH is fundamentally different than the OH from an alcohol. Why is the OH from a carboxylic acid different from an alcohol? Not electronegativity, because they're both oxygens. Why is the OH different for an acid than an alcohol?
Acidic.
It's an acidic hydrogen. That changes the strength of that OH bond. Acidic hydrogens are in fact a weaker bond. That's why they're acidic. Because the bond becomes weaker, what happens to the frequency at which it shows up? It shifts to a lower frequency. That means the OH bond tends to overlap the CH stretches for most carboxylic acids. So you get this broad kind of nastiness happening. A relatively clean example is the top one. There's your OH, and then you probably have some CH3s that would, in theory, look nicer had I not drawn it, okay, that are showing up underneath it. Okay? And that's why the overall signal ends up looking kind of messy. We do have a clean OH bond underneath there, but because it's overlapping the CHSP3s, you don't see that nice, neat, broad OH. That's a nice, clean, typical, or not atypical example. Your typical examples show up down below. Okay, you get a broad range within your CHSP3s. Okay, lots of sharp peaks that doesn't match the patterning for CHSP3s. CHSP3 should not be this broad signal. Okay, same deal for this other one. You get kind of this broad, just lengthening or thickness, I might be the right word, for the base of that peak. Okay? you will still see that carbonyl. Usually the carbonyl tends to show up very intense and very broad, or not very broad, but broader than most carbonyls. Okay? So be aware of that when you're looking at the spectroscopy for IR, for carboxylic acids. For NMR, your carboxylic acid shows up at about 12. Okay? And one of the big things that's kind of problematic here is notice that the mite is written in there, and the mite is written in italics. And not only that, I even then say, why mite? Why would it not show up? If it's acidic, what has it done? It left the structure. If it's no longer attached to the structure, can I see it anymore? No. Okay? So the reference for that is labile. It can come on and off the structure. Labile, I think, just means move is the root. Okay? So you have a hydrogen that is easy to move. If it is easy to move, it may or may not show up on the spectrum. In this case, we're seeing it show up kind of nicely, okay, at 12. Usually that's pretty rare. Okay? For the most part, they're almost impossible to see until you do a massive zoom in on the spectrum, and it's a blip above the baseline. Okay? The carbon-oxygen pi bond for your carbonyl shows up a little bit under 200. Why would it show up less than 200? Aldehydes and ketones tend to show up right at 200. Why would the carbonyl for a carboxylic acid show up a little bit less than that? It has resonance. What is that resonance doing to the pi bond? It weakens the pi bond. As it weakens the pi bond, it starts to approximate more of the carbon-oxygen single bond, which shows up at a lower frequency. And that's why it shifts to lower frequencies. Okay? So there's kind of your whirlwind, big things to get out of your NMR and your IR as far as spectroscopy. Okay? Which then takes us to the next fun part. Okay? Carboxylic acids are looking at acid and base strength. Okay? And this tends to be the big part that gets tested in second semester. In first semester, you see a lot of reactions, rank the acids. Okay? In second semester, what ends up getting thrown in there is rank the bases. So you have to be a little bit more careful because you're now ranking a different thing. Okay? Do the rules change? No. The rules that we use to evaluate both acid strength and base strength would be charge, size, electronegativity, resonance, induction, and then craziness if you got to deal with it. Okay? You need to be able to use those rules to evaluate the stability of the individual pieces. When we go through and look at acid strength, typically we rank our acid strength based on
The negative charge
if we take off the hydrogen. So when we look at acid strength, we rank them based on the stability of the conjugate base. Why, when I look at the strength of an acid, would I look at something that's not the acid? Why am I evaluating the conjugate base to predict whether HA was an acid?
Because if the base is large, it will tell you that it can hold more hydrogen.
So again, that's fine. Why am I looking at the base though? Yes, if the base is large, it can stabilize that negative charge. Why look at the base? Why not just look at the acid and say, well,
Because if the base is not stable, the acid won't give up that hydrogen.
okay, well, you're still referencing the base.
You're referencing the base, huh? You said, why am I looking at the base? So
Why, well, exactly, why are we looking at the base? Which of these is the stronger acid? HA red or HA purple? Can you tell that's purple? Those are different colors.
Can't tell until you look at the conjugate base.
Why can't you tell until you look at the conjugate base?
because it's neither of them are charged.
What are you evaluating?
A bad resonance. They were active.
Stability of what?
We have to evaluate who has
Okay, what's the charge?
the
Electrons. We're looking at the conjugate base because we're looking for an explanation for the stability of the electrons. Okay? Why can't I look at HA to find the electrons?
Because they gave them away.
There's no charge. Those electrons are embedded in the structure. They're very hard to kind of piece out and separate from the rest of the compound. So what we end up going through and doing is we look at the conjugate base, because the conjugate base, I can now see a negative charge. I can see how that negative charge moves, because what have we as organic chemists created as a rule set to explain how reactions work?
Charge size, electronic pattern.
How a reaction works. How do I know two things would connect to each other? How would I show that? Curved arrows. What do curved arrows show the motion of? Electrons. Okay, so what we're concerned about is the movement of electrons. Everything we've talked about is how do electrons move. So once can see electrons, we can now evaluate stabilities. We can see how those electrons move and allow us to predict whether they're stable. If they are stable, then we would expect the starting acid to react very quickly to make that more stable structure. Okay? So when we think about acid strength, we always look at the conjugate base because the conjugate base shows the electrons. Why do we not look at acids? What does an acid do? Gives up protons. Do protons have electrons? No. That's why it's difficult to look at the strength of an acid based off of the starting structure. Right? So what happens if we now switch to a base? What should we be evaluating?
The conjugate acid? But that's not going to work.
You just
Okay.
look at the base.
I could theoretically look at the conjugate acid.
We already have the base. We already have the charge.
I already have in the base what?
The electrons there.
The electrons to evaluate. So when we're thinking about ranking bases, we typically do not need to look at the conjugate acid because our base starts with the electrons. That's what we're trying to predict stability of, is those electrons. So bases can be more straightforward to solve for because you look immediately at that structure. How are those electrons distributed? If those electrons stay in the structure, can it act as a base? What must a base do? Give up electrons. If the electrons stay in the structure, can it act as a base? Shaking your head, no. Why? The base, by definition, must donate them. If the electrons stay in the structure, they can't donate. Okay? So students tend to mess this up because you've memorized a pattern within acids, and you get forced these patterns in Gen Chem for acids. And then all of a sudden when it switches to bases, you think it's a whole new rule set. It's not a whole new rule set. Focus on what you understand about the electrons. This is why electron motion is so important. Kind of makes sense? Okay. The two classic examples that come out of this, particularly for second semester, the first one, our big proton donor, ends up being the carboxylic acid. Okay, or in this case, the acetic acid. The proton acceptor, or our base, our classic example tends to be amines. Okay? The perfect storm of these two functional groups comes into play in biochemistry. Like, really? Where we would take, say, an amine and a carboxylic acid, which are difficult to process in and of themselves, and we take both of them and we put them where? Together to make an amino acid. All of our protein structures, okay, are based off of the balance between these two functional groups. Okay, so you have to be very careful understanding acid and base chemistry whenever you're dealing with both of these functional groups. Okay, how would you evaluate those structures? Yeah, these. Really any structure. What would you need to look for?
Where are the charges? You have to do
Charge.
first.
We would look for charge, size, electronegativity, resonance, induction. Okay? Stop getting questions wrong and I won't keep making you regurgitate that. Okay? There's the fair trade. Okay? So, make sure that when you're looking at acid-base reactions that you know you're only looking at an acid-base reaction. In both of these equations was the only thing that changed the location of a hydrogen. Okay. And the top one, what happened? Okay. The alcohol shared a hydrogen, or the alcohol grabbed a hydrogen, putting the electrons onto our oxygen. We end up with the lone pair, now left on water, and a new bond to hydrogen. Because we picked up that new bond, our original starting oxygen had its octet, was neutral. What did it do? It shared electrons with somebody else. So it lost electrons. If it was neutral and loses electrons, it should become positively charged. All right? What happens in the bottom case? What's the most reactive thing? The what? The hydrogen. Why is the hydrogen the most reactive thing? Because that is literally hydroiodic acid. And if I compare hydroiodic acid's reactivity and say to a strong acid like, I don't know, hydrochloric acid, hydroiodic is stronger. Okay? The most reactive thing here is actually that H+. What's the first thing that happens in this reaction? The pi bond takes the H. The electrons go to the iodine, which would be? We would consider that as an acid-base reaction. Notice that more stuff happened. The iodine has also connected to this. I'm not showing a mechanistic step here, I'm showing a reaction step. In this reaction, what I've done is an addition. Okay? This one's officially an electrophilic addition. Why would we call it an electrophile addition and not a nucleophile addition?
Well, the nucleophile addition, the nucleophile usually attacks, but in this case, we have the electrophile, which
In a nucleophile addition, when I do the addition, the thing that reacts is a nucleophile attacks the pi bond. What happened here? The pi bond attacked, and this is where I kind of disagree with Cardy's labeling. The pi bond attacks a positive atom. Positive atoms are electrophiles. So this is an electrophile addition. Okay? Addition reactions are always dangerous because if you look at the end result, what things were added? A positive thing and a negative thing. But the order in which those pieces were added makes a really big difference to the mechanism. Okay? When do you see electrophilic additions? Non-polar pi bonds. When do you see nucleophilic additions? Polar pi bonds. So again, if you can come up with those classifications, you can start to whittle down what reagents you need to be using in each of those cases.
how is this electrophilic?
This one's electrophilic, yep.
Isn't the pi bond
The pi bond is reacting first with
the acid?
okay, hydrogen, which is what charge? What things are positive?
Electrophiles, but how
There's
is
your
it
electrophile addition.
electrophile addition? Because they're nucleophile.
Could we show this as a nucleophile addition? Okay, this is the important distinction to make. Okay, our alkenes can only act as nucleophiles. Okay, we have some gray areas there. Okay, but for the most part, our alkenes only act as nucleophiles. If they act as a nucleophile, what are they going to react with? Electrophiles. By definition, alkenes will only do electrophile addition. How can I get it to be a nucleophile addition? Make it a polar pi bond. This structure will never do a nucleophile addition because it's not an electrophile. Okay? So we have to be careful by looking at those definitions and trying to categorize them. Okay? So this just summarized all of those rules. Right? In theory, I did it right, so we could go through and look at these. Right? When we're looking for our stronger acids, we're looking at the conjugate base. So we can add that word on here. We're looking at conjugate base. The conjugate base should be less negative. So a stronger acid, and I even left the charge off, unfortunately. The stronger acid will generate the less negative charge. Right? After that, the bigger the conjugate base, the stronger the acid. Why? If it's bigger, what does that do to the charge? Distributes it, it stabilizes it. It makes it less negative. Electronegativity. The larger the electronegativity, the stronger the acid. Why? Because the conjugate base can hold the charge. It's making it effectively less negative. Okay? So each of these have interpretations off of them. Resonance, you'll notice, has two categories. Why might resonance have two categories? Can you have a resonance structure make something less stable? Yes. And if you're wondering about that, go back and look at exam 1. There's test questions that reference those. Look at practice exam 2 before Wednesday. We have questions that directly reference those. Okay? The blue side, we're looking at the base. Here, we're not looking at the conjugate. We're looking at our starting base. I don't know how else to say that other than starting base. Okay, we call it home base. Some people laughed. Okay? Stronger base means more available electron. Are people slowly getting it more and more? More available electrons. Size. Okay? The smaller it is, the stronger the base. Why? That charge is spread over a very tiny area, making it effectively more negative. Note that it's different between acids and bases. This is why second semester they like to ask base questions, because what did you do all first semester? You memorized the acid rules. That's why you shouldn't memorize. Okay? They're intentionally switching it up to make it more confusing for you, because what you did was try and make a shortcut. Okay? Shortcuts work once or twice. Eventually they come back and haunt you. Okay? Make sense? Okay. So, ranking acidity, those top two structures, which one do you think is the stronger acid? You're pointing to, so I got the verbal cue and then the signal cue made it difficult. Okay, the left structure. Why is the left structure more acidic? Okay. There are multiple kind of ways to sneak your way through this. The name of that functional group is literally a carboxylic acid. That's probably a big tip-off that that one's an acid. Okay, and largely going to be the more acidic structure. So for instance, if you saw a functional group along these lines and compared it to, say, something along these lines, which of these would be more acidic? The one on the left, which is known as carbonic acid, is the stronger acid than the diketone.
But isn't the resonance, because there's way too much, it's destabilizing?
Does the red structure stabilize some resonance? Yes. Or sorry, they're both red. The carboxylic acid still has resonance. Okay? And one of those resonance structures is slightly destabilized, but not destabilized enough to counteract a negative charge on a carbon versus oxygen. Okay? The carboxylic acid is by far the stronger acid there. So you have to evaluate first and foremost the atoms that hold the charge. The atoms that hold the charge on the left structure there, oxygens. The atoms that hold the charge on the right structure, oxygen and carbon. Okay? So, if we get back to the question we had, you said the one with the red underline is the stronger acid, and you said because it's a carboxylic acid. Now to a better answer. Why is it the stronger acid?
Well, we both are charged.
Okay. If we removed the hydrogen, because we're being asked to rank acid strength, they'd both be negatively charged. Okay. Why can oxygen stabilize the charge better than the nitrogen? Okay. We start with charge the same. The next thing would be size. They're in the same row, so no difference. We move to electronegativity. Oxygen is more electronegative than nitrogen, meaning don't bring reactivity into it. What is it doing with those electrons? It's holding them tighter. If anything, it is actually less reactive. Okay? The next kind of fun thing that could go with this, the carboxylic acid has resonance. Does the amide? Can this do resonance?
Unfortunately, yes.
Okay, so number one, before we get into the resonance, do we care about resonance?
No, because
No. We've already evaluated the difference. The difference is that the oxygen can stabilize that charge better. It's going to trump. Okay, the resonance that we're generating is the same in both cases. Okay, so the resonance is not a factor in the evaluation here. We've already established that electronegativity differentiates these two. Okay, can the amide do that resonance? Not very well. Okay, we're in perpendicular orbitals. It still maintains that other lone pair. Because it can't hold on to the electrons quite as well as oxygen, that resonance structure is not a very good contributor. Okay? And we end up not seeing a very large resonance stabilization. It's present, but it's tiny. Okay? Middle three. Which is the strongest acid? Which is the middle strongest acid?
is that a fluorine?
Yeah, I made it a weirder question. Yeah. Okay, we got to suggest the left structure is the middle one. The middle strongest acid. So, to evaluate, what are we doing? We remove a hydrogen from each of these structures. Negative, negative, negative. Now what do we do? Charge. It's the same size, same induction, or sorry, not induction. Resonance, electronegativity, all the same until we get to induction. The induction is now looking at a molecular electronegativity effect. Okay, is there an electronegative atom somewhere in the structure causing the electrons to get pulled into the structure? Yeah, we have fluorine here versus what's in the next one?
Hydrogen.
Hydrogen is our fair comparison. Okay, and then the last one, it's two fluorines. Okay, so fluorine versus hydrogen, which one's more electronegative? Fluorine, which means what is it doing to the negative charge? It's pulling it into the structure more. Meaning when I compare structure 1, 2, left, middle, which one's the stronger acid? The one on the left, because the electrons are getting pulled in, stabilizing that more. Okay?
Can we repeat what you just said?
The one on the left is the stronger acid because it is a more stable negative, because the fluorine is pulling that negative charge into the structure more than hydrogen is.
But I thought the middle one would be the strongest because carbon is not being pulled on.
The carbon is not being pulled on. Okay? What does that mean? So we're talking about this negative. This carbon's not getting pulled on. So is it doing anything to this one? Nope. Is it doing anything to this one? Nope. So everything just is. What happens here? Is that carbon getting pulled on? Yeah. What does it want to do now that it's getting pulled on?
Stabilize itself.
Stabilize itself by doing what? Yes, Mari? Pulling electrons from that carbon. Well, now this carbon is losing electrons, so what does it do? Pulls on electrons nearby. What happens to this carbon? It's getting electrons pulled away from it, so what happened to it? It's becoming more positive, so what does it do? It pulls this negative charge into the structure. If it pulls the negative charge into the structure, what did we do to the negative? Stabilized it. The more stable this species becomes, the more acidic the original structure was, because we're looking at the conjugate bases.
Can that happen on the very right side?
I didn't talk about the very right side yet. Okay, so we only evaluated the first two, which is an important distinction. When I went through and did all of these, or really, since it's only two examples, we're only looking at two structures at a time. We do not bring in three structures at a time. Why? I heard someone mumble, it's confusing. It's confusing to bring in multiple things. Compare only two things at a given instant. Once you finish that comparison, bring in the next one. Okay? In this case, I'm not going to compare the middle structure to the far right. Why not? I've already established the left structure was more acidic. Since I'm trying to find more acidic ones, I'm going to take the champion of that battle and compare it to the next one. Make sense? Okay, what's the difference between left and far right? More fluorines, which means more pull on the electrons, which means more electrons come into the structure, making the far right the most stabilized, which would make that one the most acidic. If we go all the way back to the original question that I asked, which was? Which one was the middle acidic? That's why we've got that red one underlined. Okay? Each of those stages should be things that you are processing, and you should be writing that information down. It takes time, it takes practice. If you're out of time, do as much of it as you can in your head. Last one. Or should we do more?
Yeah.
Yeah? Okay. This one actually has competing effects. I don't want to talk about this one until we talk about aromaticity.
No.
Actually, we need to address aromaticity first, and that's not this unit. Okay. So, carboxylic acids, amines, and then we're looking at acids. How would we evaluate acid strength? If I said, here's a solution, what could I tell you about that solution to give you an idea about the acid strength?
pH.
I could tell you something about its pH. Okay, we could do titrations. For those of you in the lab and happen to draw the lucky straw, you get to do a titration. pH, we could look at pH. Okay? pH is going to become really important when I take a carboxylic acid and I take an amine and I put them next to each other. Come on. And what we now have is an amino acid. Amino acids have two acid-base characteristics, which means when I change the pH, I'm changing the baseline level of the acid-base structure, which means what happens to this structure? It gets protonated or deprotonated. Well, that's it. That's not that big a deal, right? So let's see. Oh, I decided to keep it simple. Okay, so let's test it. The fun question that comes out of this, at pH 2, what is the charge on the structure?
Minus.
Okay.
Is there a way to tell?
Is there a way to tell? Absolutely, there's a way to tell. pH 2, what is charge?
There is no charge, it is as it is.
So,
It gets protonated.
to give you an idea of answer choices,
The amine is protonated.
okay, we could do, whoops, a -2 and a +2. Do something like that. Okay. What does it mean to be a pH of 2? You are in an acidic environment. Okay, there is an excess of H+. Okay? When I take a look at the amine functional group, how does an amine act? It acts as a base. What kind of environment am I in? Acidic. So what should the amine be? I should protonate it. Because it acts as a base in an acidic environment, I should add a hydrogen. Which means what happens to the lone pair? It goes away, and I put a hydrogen on it. What charge would the nitrogen now become? Positive. What happened to the carboxylic acid? What is the reactivity of a carboxylic acid? It is acidic. What's going to happen to an acid in an acid environment? Nothing. It should stay in its base state, which means it's fine. What is the charge on this structure? It is now a +1. Okay? Because we get some people that sound like they've got this, probably because they've studied some MCAT questions. pH of 6, is that acidic? Yes. So I am still acidic. Does that change anything? So it becomes really important now to know about the relative acidity and basicity strength of the amine and the acid. This is why it is important to know pKa's. The pKa of the amine is about a 9. The pKa of the carboxylic acid for an amino acid is, oh yeah, you're right, it is 2. Right? Yeah. So if I'm at a pH of 6, okay, am I more acidic or less acidic than my amine? Okay. pH of 6 is lower on the pH scale, which is more acidic. Should it be protonated? Yes. How about the carboxylic acid? Okay. I'm at a pH that is higher in pH than my pKa, which means I'm more basic than my pKa, which means deprotonate. Remove the hydrogen. If I remove the hydrogen, what charge does the oxygen become? Negative. Okay? What does that then mean? The charge is 0.
It's 0 because it's balancing out.
Because the overall charge in the molecule cancels out. This is known, for fun fact, as a Zwitterion, okay, or twin ions. Okay? For those of you that have to move into biochemistry, unfortunately I didn't put the slide in, but it's like my favorite slide from when I teach biochemistry. Anybody know what S is? Biochemistry. Serine. C. Cysteine. Alanine. Arginine. Tryptophan.
No, I was talking about
Oh, so it's tyrosine then? Okay. Because this is literally a valid protein. What you could be asked is, what is the charge on this molecule at pH 4? Okay. To evaluate that, you would have to know that the structure for serine, is it 2 carbons? Or is it just 1 carbon?
2 carbon.
You would have to know, and then that cysteine, it's the sulfur one, right? Alanine, I always get alanine and glycine confused. Is it just hydrogen?
Alanine is just gonna.
See, I can never get that one right. Arginine. There's some nitrogens. I think it's this one. It's usually written out as that, right? Something. Okay. So you would have to know the base structure for each of those pieces, and then you'd have to know how do they change when we change the acid-base strength. Okay. For those of you that have to take biochem, that is what you will have to do. That will almost guaranteed be a test question. Okay. Not that protein. Nobody but me would do that, because nobody but me thinks that's funny. Okay. The thing that you can use to kind of cheat your way through this is if the pKa is lower than the pH, then remove the hydrogen. If the pKa is higher than the pH, then keep the hydrogen. This tends to work really well for the carboxylic acid. It doesn't work so well for the amine, because what most students will do with that amine is they say, well, if it says to remove the hydrogen, then I should end up with this structure. The problem with that is now insanely basic. So basic, we would die. Okay? Literally. Okay? We have to be aware of the leveling effect that was talked about in first semester. You can only be as strong an acid or base as the environment you're in. When we look at amino acids, what environment are they in? Water. So water is what's going to dictate the strength of your acids. I can't have a negative nitrogen in water. That nitrogen would immediately deprotonate water to get me hydroxide. Okay? So you have to be a little bit careful with the protonation, deprotonation states for your amines and your acids, but that will show up if you have to take biochem, and it absolutely shows up, as you might be able to already tell from people that have already taken the MCAT or started to study for it. It shows up as a biochem test in MCAT kind of things. Okay. So polar pi bond with a leaving group attached. Okay, so we now have a new functional group. Our nucleophile can do what? It can attack the carbonyl carbon. Why would it attack the carbonyl carbon? Okay. That carbon is partially positive because we have that polar pi bond withdrawing electrons. Okay? We then form this special structure. That special structure is known as the tetrahedral intermediate. Okay? You can see questions specifically referencing the formation of the tetrahedral intermediate. Okay? And we'll address why we might need to see that in a second, because now what happens once we form the tetrahedral intermediate? The leaving group does not leave. The electrons come down to reform the pi bond, then kick out the leaving group. Okay? And we end up with our new functional group and a leaving group at the end. What's going to drive this reaction?
It really depends on the nucleophile.
It very heavily depends on the nucleophile versus the leaving group. If the leaving group is more stable, and I don't just trust me that means more stable, what does that mean?
The reaction is bound to happen.
Okay, reaction is favored. Let's just say products. Wow, there's too many A's in favored. If the nucleophile is more stable than the leaving group, now what happens? We would get no reaction or reactants favored. Okay? So when we go through and look at each of these reactions within this section, that's ultimately what you're being asked to do, is to compare those two to each other and decide which one is more stable. Okay? That's the bottom line of the next two chapters. That's pretty much it. Okay, we throw in some special reagents to make things look cool and do some kind of neat, fancy looking things, but that's really it, right there. Okay? The next part that I want to address is I'm going to clear everything away. If we just look beginning to end, what does it look like happened?
It's an apple substitute.
Okay. This looks like just a standard substitution where what happened? The nucleophile attacks and kicks out the leaving group. Notice if that's the case, do we have an intermediate? No. Okay, so this is why the tetrahedral intermediate gets tested on, because the gut instinct, if someone doesn't pay attention to what's going on with the mechanism, they assume a substitution. Okay? The other reason why they tend to ask questions about the tetrahedral intermediate is that we get insanely lazy about drawing this mechanism, particularly within this unit. I'm going to be making these same lazy mistakes. The nucleophile attacks, then what happens? Nope. I break the pi bond by shuttling the electrons up to the oxygen. Then what do? Then I reform the pi bond. And then I kick out the leaving group. And I would show all of those arrows in one single structure, which is messy and horribly wrong. Okay? It is split into two mechanistic steps. You need to be aware of that. You also need to be aware that we will make this shortcut for the sake of time. Is that a question?
Well, I'm just curious, like, why can't it just attack and leave it the same? Is that just how it formed? Like, how do we?
So, getting at the details of how that mechanism happens, we have evidence that the tetrahedral intermediate exists.
Okay.
So, because we have evidence that it exists, we should be showing that mechanism. Okay, because guaranteed, one of the first suggestions is going to be what for a mechanism? It comes in and kicks it out. I'm done. Let's do that. We test it and prove that there's a high concentration of that negative oxygen. The only way that happens is if we break the pi bond. Okay? We should be able to use bond strikes to explain why that is not the best mechanism. Why it actually makes more sense for the nucleophile to attack here and break the pi bond than to break the leaving group. Why does it make more sense to break that pi bond? What's higher in energy? We're breaking a pi bond which is higher in energy than the sigma bond, which means I should break the pi bond first because it's higher in energy. If I can then reform it, then great, I can reform it, and then I can break the sigma bond. Okay? So we can use those rules of energetics that we talked about way back in first semester to explain what's going on with that. Okay? The next part is what are those leaving groups? Okay? Notice that we've got a whole bunch of structures drawn up here, and within that list, I have not shown a ketone. Why not?
We're not dealing with that anymore.
What's that?
We're not dealing with that anymore.
I don't accept that. Carbon's a bad leaving group. Okay? So we're now moving to the nucleophile addition elimination. I need to be able to do an elimination, and to do an elimination, what do I need? A leaving group. Is that carbon a leaving group? No.
Make it into one. If you add variance to it.
Yes. Yeah. Okay. So there are ways that we can make that carbon a better leaving group. For the most part, we stay centered on these functional groups. Okay. So we're starting with the acyl chlorides. Okay. Remember that functional group was the acetyl. As a class, we can reference them as the acetyls, and we can do whatever we want out here now. Okay. It's still an acetyl or an acyl chloride. The next one is an anhydride. The next one, let's just say anhydride. The next one's an ester, followed by amide, followed by a carboxylate. Okay. Which of those do you think, or where's the leaving group in each of these? They're all on the side. Which side? Right side. Because, believe it or not, your instructor's a human and tried to unintentionally mirror them so they all showed up evenly. We're looking at chloride versus this whole piece. The next one, the OR. This one. This one. Anybody else notice anything convenient about this order? The ability to act as a leaving group. Chloride is a very good leaving group. Why would chloride be a very good leaving group? What does a leaving group need to do? Stabilize the negative charge. Chloride's a great leaving group because it's big. It can stabilize that negative. When we move to the anhydride, what's the leaving group? Right? If we look at that piece, we're saying that that atom takes those electrons, right? So that oxygen would be negatively charged, right? What functional group would that be? It's a carboxylate. How reactive is a carboxylate? Where is it on this list that you just said showed stability? Very bottom. That carboxylate is an insanely good leaving group, which makes it very, very stable, which is why the carboxylate itself is not susceptible to nucleophilic attack. Okay? Why is it a very good leaving group? The oxygen is more electronegative, so it can stabilize the negative charge, and there's a resonance effect. Okay? We move to the ester. Why is the ester less good of a leaving group? There's no resonance. We move to the amide. Why is the nitrogen less good of a leaving group? Okay. Nitrogen has a lower electronegativity than oxygen, which means it can't steal the electrons as easily. Why is the last one really, really horrible? It's charged already, so that if it left as a leaving group, it would be even more charged. Insanely unstable. Make sense? Okay. Could we go through and change these conditions? Well, actually, first, which conditions are we under? If we're under acidic conditions, what is there a surplus of? Hydrogen ions. What charge are hydrogen ions? Positive. What charge do we have floating around? Negative. Are we under acidic conditions? No. We're going to be running under basic conditions, and we know that because we see negative charge. Okay? Could we run under acidic conditions?
No, not negative.
Can we change the reaction, the mechanism, such that we could run under acidic conditions? Yes. Okay? We do tend to favor basic conditions because we get what kind of nucleophile? Strong nucleophiles. Okay? So those are our primary functional groups. We can look at reactivity. We'll look at energy diagrams on Wednesday after we do the exam 2 recap. Okay? So with that, we are done.